Hi everyone and welcome back to Matter for Thought. The guest for this episode is one of the smartest people on YouTube, Ph.D. Tony. I am truly humbled to host you here.
In the previous episode, we talked about fictitious forces, and we noticed that there are differences between the way a physical system seems to behave according to those people who are inside the system as opposed to those who are outside the system. Today we will talk in more detail about this concept of inside and outside, or as they're more generally called, frames of reference. A reference frame is defined by a choice of origin. This is a unique reference point against which the position of velocity of every other object within the system may be defined using a coordinate system. All of that sounds very abstract and very mathematical, so let's illustrate it with a simple concrete example. Take, for example, a car at the head of a column of traffic at an intersection. We can then set our origin to be the centre of mass of the car and describe the position of everything around it in relation to that point. Now we need to define a coordinate system. So we start by defining the x-axis. We can set forward in front of the car as the positive direction on the x-axis so that the car behind our original car is 5 meters in the negative x direction. We can then define a y-axis so that the car on the left is 3 meters in the positive direction in the y-axis, and so on. We can define the position of everything within our physical system in relation to our origin. As long as everything is stationary, it's very simple. But what happens when the cars are in motion? As we mentioned in the previous episode, velocity is a relative thing, and as long as there is no acceleration, and hence no fictitious force is felt by anyone, it is impossible to determine by observation alone who is stationary and who is in motion. In such a situation, we just take the origin with us. This concept is quite trivial. Galileo understood it back in his era and formulated a simple way to relocate the coordinate system between objects that are in motion at a constant velocity, no matter what their direction of travel is. Until half a minute ago, we treated the whole space, position and velocity according to this car. Let's call it A. If you want to redefine everything in relation to car B, all you have to do is subtract the position of car B in relation to car A from the position of everything else in the area. Have you lost me? Well, let's see how it works. Suppose we have 3 cars. Car A, whose position is at the origin, car B, which is 3 meters to the right of car A in the positive direction on the y-axis, and car C, which is 4 meters ahead of car A in the positive direction on the x-axis. So what is the position of car C in relation to car B? The coordinates of car C relative to car A are simply 4, 0, minus 0, 3, which are the coordinates of car B in relation to car A. So that gives us new coordinates of 4 minus 3. These are the coordinates of car C in relation to car B. Simple. This technique also works when you want to calculate relative velocity, not just position. All you need to do is subtract the velocity of the new car from that of the original car. If they both move at the same velocity, just like the first example we gave, we get a relative velocity of 0, which makes sense. And when the velocities are different, the mechanism of the transformation is still exactly the same. In the next episode, we will start to deal with a topic that flat earthers don't understand at all: trigonometry.
Thank you very much. In your voice, it does sound better. And that's for today, friends. I hope that clarified the unclear topics from the previous episodes, and there is nothing complicated here. All you need to do is subtract the new from the original. Before I wrap things up, I want to thank my patrons. If you find the content good and the cause worthy, link to my Patreon is in the description. Feel free to like and share, add a comment, and subscribe if you like to. I was, as always, rndthinker, and I'll see you in the next video.